All right, in today's lesson, we are going to be exploring the properties of exponential functions. So we are going to be looking at properties of their graphs and how the graph represents the different constraints on the equation of an exponential function. So this is a little introduction activity, which I'll let you guys do on your own. Okay, so you'll need one piece of paper for this, and you are going to fold it the number of times here, and you're going to count the layers and put the layers here, and then you are going to then represent the number of layers as an exponent of base 2. So for example, I'll do the first one with you. If you have no folds, then you would have, of course, one layer. So there would be one layer. And how do we write 1 as an exponent with base 2? Well, remember, an exponent is something, essentially it's repeated multiplication. So for example, 2 cubed would be 2 times 2 times 2, which is 8. So then how do we represent 1 as an exponent raised to the base of 2? Well, you should remember from grade, essentially, I think it's grade 9 math, that any base raised to the power of 0 is equal to 1. So 2 to the power of 0 would equal 1. So essentially, the exponent would be the number of folds. So 2 to the power of 0 is 1, which means if you fold the piece of paper 0 times, you'll have one layer. So I'll let you continue on the rest and see the pattern. Okay. So basically, one thing we'll fill in here is that when you have an exponential equation, the variable, as you can see, x is in the exponent position. Whoops, wrong spot. The variable is in the exponent position. Okay. So essentially, when we look at the characteristics of exponential functions, we're looking at y. Sorry. Insert an equation. So you would have y equals a times b to the power of x, where a is a coefficient and b is our base. So a is a coefficient, b would be the base. Let's make this red. Okay. So essentially what we're going to do is not use a graphing calculator. I should have changed the notes. We are going to use Desmos instead to complete, to get the graph. So I'm going to let you guys fill in the data tables if you want. Okay, but essentially we're just going to take this graph here, this equation, and we'll plug it into Desmos. So our first equation is y equals 6 to the power of x. So y equals 6. To get the power of, we use a to the power of b, so it puts it in the exponent position. So y equals 6 to the power of x. And you can see here that the graph kind of approaches 0, the x-axis, as we go to the left, and then it swings up, and it has a y-intercept of 1. Okay. And then we can see that it increases. So essentially this would be a picture of the graph. It sticks in quadrant, goes from quadrant 2 to quadrant 1, and you'll notice it does not go below the x-axis. So the y values are not negative. So we can again snip this and we'll put it into the we'll put it into our Word doc. So I'll just snip a little bit there. There we go. Copy that. We'll paste it here. Make it smaller. Okay. Alrighty. So the number of x-intercepts would be none. It does not have any. So that's very important that you notice that exponential functions do not have x-intercepts. The y-intercept in this case is 0, 1. 0, 1 is the y-intercept. The end behavior, it goes from quadrant 2 to quadrant 1. The domain, as we can see back here in Desmos, the x is going to go to negative infinity to positive infinity. There is no restriction on the domain. So the domain would go from negative infinity. So negative infinity, insert infinity symbol, positive infinity. Let's copy that. Make that red and bolded. Okay, the range, you can see that the y value doesn't go below 0, but then it never ever touches 0. So it would be going from 0 to positive infinity, but it would not include 0. So it would not be inclusive. Therefore, you would need a round bracket. And it would essentially go 0, comma, infinity. That would be the domain and range for our first graph. Okay, so again, we only had a base. So we assumed in this example here that the a value was 1. So let's see what happens when you actually have a coefficient. In this case, it's positive 3. So we'll go to our Desmos and we'll reset it. And so we type it in exactly as we see, y equals 3 bracket, and the base, if I remember, is 2. So 2 is the base, and click on the outside of the bracket, and we are going to raise it to the power of x, a to the b x. And you can see here that the graph changes a little bit, but it's still the same shape where it doesn't go below the x-axis. It approaches 0 as a minimum value, but never reaches it. And then it swings up in quadrant 1. The y-intercept is 3. Interesting that the coefficient is 3. So just a quick learning thing here. If we put a in a slider, okay, if a is 1, the y-intercept is 1. If a is 5, the y-intercept is 5. So we would also consider this to be the initial value. So a would be the coefficient or the initial value. If a is negative, you see that the graph swings down and it's still the initial value. So if it's negative 4.8, then the y-intercept is negative 4.8. So it's worth noting here that the coefficient is also known as the initial value. Okay, so back to our second example. Instead of a, it's 3. So we've got our graph, and again, we'll do a little snip. Just enough to catch the y-intercept there. Smaller. Okay, So again, you can see here that there are no x-intercepts, so none. And the y-intercept in this case is 3. Notice that the y-intercept would be equal to the coefficient or the initial value or the so-called a value. The domain and range would be the same. The domain is negative to positive infinity and the range is 0 to positive infinity. So the domain and range would be the same as the first example. And we notice it's interesting because it is this exact same graph. The only thing that's different is that the initial value is changing, or the y-intercept is changing, and it's not as steep. Here you notice that this graph is steeper. It's because that the base is bigger. 6 is larger than 2, so it is a larger base. Notice though that the graph does swing up. It's increasing, okay? And it still goes from quadrant 2 to quadrant 1. Okay, so notice that these bases 2, 6 are greater than 1. Look at these bases here, 1/2 and 1/4. Those bases are between 0 and 1. So let's see what happens then when we have a base between 0 and 1. So we'll go to Desmos and we will reset our graph. Our third example is y equals 1/2 to the power of x. Y equals bracket 1/2, so 1 over 2 or 0.5, and then to the power of x, so a to the b, x. And look what happens to the graph. Okay, the graph, it switches directions. Whereas when the base was greater than 1, you notice that the graph increased as you went left to right, the y value gets larger. Now, when the base is between 0 and 1, as we go from left to right, the y value gets smaller and it reaches 0 but never touches it. So it's kind of a reflection here. If we looked at y equal 2 to the power of x, just as an example, you'll notice that it's a mirror image. It's just been flipped. So the base bigger than 1, we call this an increasing exponential function, or we call it a growth curve. And the base between 0 and 1, as you can see, as we go from left to right, the y value gets smaller. We would call that a decreasing exponential function, or it's also known as an exponential decay model. If you've taken biology in grade 12, you would have learned about growth, population growth, okay, and population decay. And these exponential models kind of match that. So that's a little bit of a curriculum connection to biology, but we'll close off with 2 to the x, and we'll look at the characteristics. So we would expect that there is a 1 in front of that half. So the y-intercept, of course, is 1. It's the initial value. So we will snip this just enough to get our intercept there. Okay, and we'll copy it and paste. Okay. So again, there are no x-intercepts. So there's some kind of pattern going on here. Exponential functions do not have x-intercepts. They don't have roots. The y-intercept, as we saw, was 0, 1. It still goes from quadrant 2 to quadrant 3. I mean, Q2 to Q1. The domain and range. The domain is still going from negative infinity to positive infinity, and the range goes from 0 to positive infinity. So it's the exact same. Does not change. It's just the graph flips and it's going down instead of going up. Okay, our last example here is 2 times 1/4 to the power of x. So our coefficient is 2. We would expect a y-intercept of 2. The base is 1/4. So we're going to expect that it's going to be a decreasing graph. So let's take a look. We'll reset Desmos. So y equals 2 times 1/4, so 1/4, or you can go 0.25 if you want, but y equals 2 times 1/4 to the power of x. And you'll notice that the graph, again, is decreasing. Initial value is 2, y-intercept is 2. So you can definitely make that connection. So we'll grab this graph here and put it in our Word document. Make it a bit smaller. There we go. So just like all the other three, there are no x-intercepts. The y-intercept is 0, 2, because of that coefficient was equal to 2. It goes from quadrant 2 to quadrant 1, and the domain and range are the same as the other three, the domain being negative to positive infinity, and the range going from 0 to positive infinity. So quadrant 2 to quadrant 1, and the domain and range would be the same. So notice that there are two types of exponential functions, and we'll summarize the common and unique characteristics of both of them. So we have the first two examples where the base was bigger than 1, and the second two examples the base was between 0 and 1. Okay, common characteristics. If the base is greater than 1, or if the base is between 0 and 1, there are none. There are no x-intercepts, so none. That is very important to note about exponential functions. They do not have x-intercepts. The y-intercept, okay, would always be equal to whatever that first coefficient is, so it will always be 0a. So whatever that value is, that will be the y-intercept of the exponential function. The end behavior will always go from quadrant 2 to quadrant 1. Okay, it'll always go from quadrant 2 to quadrant 1, as we saw here, to quadrant 2, Q1, Q2 to Q1, Q2 to Q1, Q2 to Q1, Q2 to Q1. The domain, well, negative to positive infinity, all of them. So that will be without restriction. Okay, if there's no restriction, no context, the domain will be negative to positive infinity. And if there's no restrictions, the range will go from 0 to positive infinity. And again, round brackets around both. That's very important. Okay, so at this point, what you could do is turn to page 439 in your textbook and work through the questions 1, 2, and 3. I'd like you to complete them in this note set, so I've given you space, and just fill in the table as you go. If you want to use your own graph, like your own snip from Desmos, then you can just delete this and do it the way I've been doing it in the notes, by snipping it like this. Your choice, or if you want to do it by hand, then you can draw it by hand. Okay, so the next part of this lesson is just connecting the characteristics of an exponential function to its equation. Remember, an exponential function, as we generally have it, is y equals a times b to the power of x. And so if b is greater than 1, you'll notice that the graph is increasing. If it's between 0 and 1, then it's decreasing. That's the base. And if the a value is positive, it makes it more steep. And as the a value gets bigger, that y-intercept, as you can see, is getting bigger. So that is sort of the exponential function. It is either increasing if the base is bigger than 1, or it's decreasing if the base is between 0 and 1. Okay, so again, this is the same as before. We're just gonna plug in these graphs, these exponential equations in Desmos, and we are going to type out, or sorry, get all the different information: the number of x-intercepts, the y-intercept, the end behavior, domain, and range. Really, at this point, we don't need to graph it to get all that information, because we know that they will not have x-intercepts. The y-intercept will be equal to the a value. The end behavior is 2 to 1 quadrant, and we know the domain and range. So we really could fill in this information, okay, as is. I would like you, I will fill these in as notes, and then I'd like you to capture the graph and plug it into your notes to finish it. I would also like you then to summarize the characteristics of exponential functions. I will also refer you to a very important page reference in your textbook, just for the general characteristics of exponential functions. You would want to look, I'm just grabbing the textbook here. Page 438, in summary, and also page 448. So please make sure that you refer to those summary charts, and I would probably copy them out, or get them, basically copy that information out and make sure you know it. Okay, so I'm going to leave this for you guys to do on your own tomorrow, okay? And as well, you will be working on this assignment tomorrow. And on Wednesday, there will be, tomorrow, there will be a concept check for exponential functions, just general characteristics. So that will be put on my Microsoft Teams page. So to recap, we've explored the characteristics of exponential functions. Okay. You are working on today, page 439, 1, 2, and 3. Tomorrow, you will fill in this part of the notes, or you could even do that today, but tomorrow you will be working on this assignment here. Okay, page 449 to 451, do all those questions, check your answers in the back of the book. As well, on the Microsoft Teams, I'll be uploading a concept check for exponential functions. So good luck with your learning, and if you have any questions, please don't hesitate to email me.